Well, good afternoon. So let's continue with the last lecture. So last time I defined a cut metric and we were a bit short of time. So I didn't motivate much this definition. So I want to say a few words. Also like draw connections to some other important result, so-called regularity lemma. So if you remember last time, for every two graphons or even a kernel, which could assume positive and negative values, we defined a cut norm. So it looks the same as L1 norm, except absolute value sum in L1 norm you put on W, but here you put absolute value sign outside the integral. And you ask what is the West pair ST of two measurable subsets such that your W on average on ST deviates from zero at largest. So that like this cut norm maybe look a bit strange at first sight. So in L1 norm, you don't have any ST and you just integrate absolute value of W. And then like for graphs, we say pretty much we don't distinguish two objects if they are isomorphic to each other. And here like one way to define isomorphism of graphons would be I don't want to distinguish W, or when I change variables by applying some measure preserving transformation psi. So you can check that if you I don't want to try this definition, but basically you just relabel input x and y using this psi. This should be psi. And this, it's easy to check. It doesn't change any f densities. So it's called pullback. So w and w psi are equivalent. So to define cut distance, we are allowed to replace one graphons by kind of isomorphic copy. Yeah, and then one more operation which we had like last time. If you have a graph G, say with 1 to n as vertices, you can correspond it to graphon, which I call W of G. So you partition unit interval into n equal parts. Here I call them I1, In, and then you put adjacency matrix. Like here's one example. You have like star with three edges. One is connected to everybody else. So you put zeros on diagonal, and then whenever you see an edge, like 1, 2, 1, 3, 1, 4, you put ones. And if you see non-edge, like 2, 3, you put 0. So this will be this corner, the square. And now you may wonder why this distance is interesting or good. And so suppose I have some graph G. And as before, I correspond this graphon W of G. And suppose I can approximate this WG by some graphon U, which has very few steps. So I have graph G on a vertex set N. Suppose I have some graphon U. And so basically, okay, so my graphon of G would be, I have many steps. So this is W of G. Suppose I can, but inside U, suppose I can group vertices in some sets, usually a much smaller number, which I called V1, Vk. Such that, and I can make U constant on each square, such that it approximates this WG very well. Again, so I won't be given hardly any results, so I could be kind of informal. So graphon with k steps, k usually some constant much smaller than n. And we know that if I take cut distance between W of G and U, already they're aligned properly, then this cut norm is small. Suppose I have G and graphon U. So let's see what this tells us about the graph G. And assume that these steps corresponds to vertices. So also I can view V1, Vk as sets of vertices. So a vertex set of G is just partition V1, Vk. Just I use the same symbols for these parts. So suppose I take any two subsets S and T. So, okay, so what do I know about the number of edges between S and T? Well, I can write it, well, as the following summation. So basically, if you look at my graphon WG, so I take set S, I take set T, and the number of edges would be just I count how many ones I see in this region, and each one is a square whose side length is 1 over n. So number of edges, if I normalize it, say, by 1 over n square, then this will be exactly integral over s times t of this wg. Okay, but then I know in cut norm it's close to u. So this is approximately the same integral, but I take my step function u. But as I said, u has just much fewer number of parts, and u is constant on every part. So maybe suppose if I have part vi and part vj, then this common constant value is dij. So that's how my u looks like. Then what is this integral? Well, it will be just a sum over all ij, possible ways to choose two parts. I have k parts. Then I integrate a function which is constant, dij. And then I just have to take a measure of this rectangle, which is just product of measures of sides. So I take vi over n times mod vj over n. So somehow, what is conclusion? If you look at all this through identity, so it says if I want to have two sets S and T, and I want to predict how many edges I have across, then this approximation U gives me a very good idea. So maybe if I draw a picture, so I have my k parts, then I have some two sets S and T. Maybe I use different colors. And then, what is this approximation in the right-hand side? Well, it basically says for every pair, I see how many pairs I have across, and then I multiply by this density. So in some sense, it predicts me like distribution of edges across cuts. So maybe let me just pause for a moment. So if I have this partition V1, Vk, and I know this k-square numbers dij, then basically I can predict quite accurately how my edges are distributed. Yeah, and this may remind you, if you seen it before, so-called regularity lemma or regularity partition. There is one difference if you, so I'm be very vague, I
Excuse
won't
me.
give any definitions.
Excuse me.
There's
So there's a
question.
question.
Why mod vi over n? Yeah, because total measure of, so y is the scaling factor. oops. So just so with now I okay. So total measure is 1 in this interval. Each set. Oh wait, good question. Yeah, you are right. Yeah, just okay. So here I identify. Okay, it's a bit of abuse of notation. So maybe I should have called these parts inside kind of vi prime or whatever inside unit interval. Then here I would have just product of their measures. But then if I go back to original sites, which are subsets of 1 to n, then I just have to scale them by 1 over n. So I have k set, which partition like n points. I partition to k sets. And now if I look at combinatorial sites, not about this prime version, but back to discrete versions, total measure is 1. So if my set has mod vi points, then I have to divide by n. So like if vi is everything, then I want to have it to be 1.
Yeah, got it. Thank you.
Mhm. Mhm. Yeah, and if you look at it, yeah, it reminds you very much Semeregi's regularity partition. It's a bit different. So here, actually, it's a weaker property which we have. So in Semeregi's regularity partition, so here what we say, if I take two sets and I look how many edges I cross among all k-square pairs, sort of average over all pairs ij, and then this is good prediction. In Semeregi's regularity partition, we wanted to say for each individual pair something similar, so it's a bit stronger, or for most individual pairs. But so it's a bit weaker property, but it's very closely related. And also, even it's a weaker property, you can still get many consequences. So one result is this counting lemma. So far we saw that, like, for example, in special case, if I want to ask how many edges I have in total, then I can look at U and then get some number. I just take S and T to be everything. I allow them to intersect. And counting lemma says if I have this weak regularity partition, which means I have a good approximation in this cut norm, then also I know fairly good approximation for all frequencies. So it says that if I take any graph F, say with say m vertices, and if I take any two graphons U and W, one could come from graphs, or they need not, for every graphon, that if I consider how frequencies, home densities of F in W and U differ from each other, then it's at most cut distance or cut norm times you have extra constant factor, which is number of edges. Yes, so this lemma is not hard to prove, but probably I don't have time. So I'll just state it. And if you look for graphon counting lemma, you'll find it in Lova's book or Yufei Zhao's book. And in particular, it implies that if you have convergence in cut norm, it implies this convergence in a usual sense. When you look at subgraph densities. Let me just write it. Density convergence. Yeah, and also there's converse implication, which is called inverse counting lemma. which gives the other direction. So again, if you search it, you'll find what proves by Borg, Chase, Lovas, Shosh, and Westergombi in 2008. So this gives you the other direction. And why, just final word before I move to local limits, why these counting lemmas and partitions are useful? Well, because there's nice result by Semeredi and Fries and Cannon. So I'll take like state weak regularity lemma. It basically states if you give me like error of approximation, any epsilon, then I can find some k number of parts, which depends only on epsilon, such that every graph or every graphon, there exists a k-step graphon U, such that in a cut norm, U and W approximates W very well. And like for weak regularity, it's known, it's at most, you can take basically exponential in 1 over epsilon square. For strong regularity, it has to be at least tower. So you can prove tower, and there are some examples show it has to be tower function. But what is important that this k depends only on epsilon, which is very important in applications. So for example, just if you wanted to prove a result when you put L1 norm here, okay, you have like two variable function. Can I approximate it, say, in L1 norm by some step functions? The answer is yes, but this number of steps would depend on W. So if you want to prove like L1 norm, then you have to change order quantifiers. For every W, there would be some K, which depends on W. And for applications, having K, which depends on epsilon, is very useful. So maybe just very briefly, again, I'll be getting more vague and vague. So suppose you have a big graph G, and you want to approximate its max cut. So within epsilon. So what you can do, you can try first to find this weak regularity partition within this epsilon. And if you can do it efficiently in some way, then, well, this partition has only bounded number of parts, okay? So you can look all possible to the k different cuts. For each cut by this identity, which we had before, you can approximate number of edges across. And then like the largest one you can output as a max cut. So that's roughly, for example, how algorithmic application work. And this was a first application which observed by Fries and Cannon, who proved this weak regularity lemma and defined this notion. In 99. So just summary, like this cut distance is closely related to regularity lemma. And in some applications, yeah, it helps that your dependence is not so horrible. So it's only exponential, while in the old regularity lemma of Semeredi, it's like a tower function, 2 to the 2 to the 2, 1 over epsilon times, or polynomial epsilon times. Yeah, so that's all I wanted to say, well, add about graphons. So let me just pause if there are some questions. I know it was very vague, but somehow if you have interest in combinatorics, graph theory, and you heard about regularity lemma, it's good to keep this connection in mind.
can I have a question?
Yeah.
The step graphon is such a graphon that has finitely many values and only on some rectangles.
Yeah, so I
Which
haven't
one?
defined it yet. It's a very good question. So what is a step graphon? U. So it means I have some partition. So interval 0, 1, I can partition into some k parts. They need not be intervals, could be any measurable sets. I have k of them such that U is a constant on every product I times ij for every I and j. Also, when we talk about graphons, we can ignore a set of measure 0, so we can say almost everywhere constant. That'd be probably a more common definition of a k-step graphon.
Thank
So the
you.
picture is I can partition into some number of parts, maybe 3 of them, and of each of these 9 squares, U is constant. And since it's symmetric function, yeah, it should also be symmetric, of course. So from analysis, as I mentioned, every measurable function you can approximate by, say, in L1 norm with step functions, but the number of steps would depend on your functions you approximate. And here we could say we could choose this k, which depends on epsilon only, and it's very crucial in many applications, in extremal combinatorics or algorithms. What, any more questions? Yes, so let's finally move to bounded degree graphs. I was hoping to spend like 1 hour and a half, but so I'll just go slowly trying to explain things and see how far we get. So here we would like to look at bounded degree graphs. So what I mean is I have some constant d such that, so to every graph which we consider has a maximum degree at most d. And so, for example, I can even take d equal 3, and it's already interesting. So if you look at cubic graphs, there are lots of like questions you can ask which in the limit which still makes sense and are open. So it's the other extreme. So unlike many real networks, you could say, for example, computers and connections, usually a single computer would be connected maybe to other, like constant number of other servers by physical cables, or like different networks. Also, like these graphs, they appear like in physics. For example, you want to say Z2 is an approximation to R2, or Z3 approximation to R3. And if you look, and then you discretize, so, and maybe configuration of particles would be some sites are 0 or 1s. And you can write different models working with the two. And kind of some of them describe like real phenomena very well. So in our case, if you want to describe some processes in R3, kind of possible models could be working with some graph of Z3. So in this case, each vertex, for example, for Z2 has only 4 neighbors. For Z3, it would have 8 neighbors. And then, yeah, if you don't like infinite graphs, you just take big rectangle and work with this portion, because sort of in this case, you can say boundary is negligible, like only a small number of vertices is on boundary, or you can make it into torus, then there is no boundary issues. And so, okay, so, and again, we wanted to say, we have these graphs, D is constant fixed, the number of vertices is huge, so somehow we still want to study them, and like in particular, we want to see what theorems can we prove, and can we define some notion of a limit. So if you apply graphon limit, this usual home density, well, then basically here it be always zero. So it exists. But if you look at density of triangle, then yeah, you cannot have n-cubed triangles because every vertex is bounded degree. So you can have at most a linear number of triangles. So instead, we consider home densities which are scaled differently. So we're still interested in home densities, but then first of all, if we consider in home densities of some f, if it's not connected, then it's product of densities of two components. So we have this relation that number of homomorphisms of f in union h into g is just product of homomorphism f to g times number of homomorphism of h to g. So here we can assume that f is connected. And then in this case, the correct scaling factor would be 1 over n, or number of vertices of G. Because if f is connected, you can take one vertex, send it to the graph, you have maybe n choices. But then for every other vertex, if you do them in correct order, you have at most d choices because it's connected to some previous vertex. So correct scaling would be this. So we will denote this T star f of G, this scale density. So you look at number homomorphism and you divide by n. So it's not quite a probability. Now this need not be smaller than 1, it be some real number. And then we wanted to say that a sequence of bounded degree graphs, Gn, we call it locally converges. If for every connected graph f, if you look at these star versions, so for every n you have some real number, not necessarily between 0 and 1, if all these numbers converge. So, and maybe right away, I said capital D is upper bound. So let's say that our universe graphs which we consider, so I'll still denote it by Kelly G. Let it be all graphs such that maximum degree of H is at most D. So I don't want to give examples on this T star because I'm going to define equivalent motions right away, which is so-called R-ball sampling. So we want to define, so idea is, so here is my graph F. And here my big graph G. So instead of knowing for every f telling me how frequently it appears, this T star density, suppose I have the following information. So I pick random vertex from graph G. So this is random x. And then for each r, I tell you, I look at ball of radius r from x. And I tell you what I see as a graph up to isomorphism. So I'll tell you which one was my vertex x. And I output this ball of radius r. So here is like r ball sampling. So first one definition. So so I would like to work with graphs with one vertex as a special root. So I'll denote the set carry G1. So these are rooted graphs. So formally it's a pair graph, and x is some vertex. G coming from our universe. X is the graph. So you can view it as rooted graphs up to isomorphism. So I have two graphs. I can relabel vertices any way I want, except root has to be preserved. So, for example, on three vertices, okay, one vertex is only one graph. On two vertices, and also let me say right away they are connected, because I'll be seeing only connected graphs. So let me put it here, and also here. So on two vertices, up to isomorphism, I just see an edge. On three vertices, I could see, say, paths, and then there are like two different ways how I can put a root. Or I could have a triangle, and then, yeah, there is only one way up to isomorphism where to put the root, and so on. And now, once I have such a graph G, I define R ball. So I have G with root x. I have to tell you distance R. So I just look at the graph, I look at set of vertices which are distance R at most from x. So I take all y such that distance in my graph G between x and y is at most R. And I see what graph it induces in G. So I remove all other vertices, those the distance more than R from x. And x is my root. So this is a rooted graph. So given a rooted graph and R, I just cut everybody who's more than R away from the root. So this, and I call it R ball. And what is R ball sampling? This would be equivalent to the previous one, but would be more convenient to work with. So again, I have some graph G, which is unrooted. I have to tell you this parameter R. So it is produced as follows. So you pick a random uniform vertex of G. So you pick one at random, all vertices are equally likely, and then you output this R ball. So BGX R. So this row GR is some distribution on this set G1. So this is some probability measure. on this on rooted connected graphs, because clearly what you see is connected. Everybody is at most distance r from root. Yeah, and then so maybe now finally let's give some examples. So suppose I take a cycle of length n and I look at distance r. So what is my distribution? Well, this graph is vertex transitive. So whatever x I pick, my picture looks the same. So here I choose x, it doesn't matter. So this measure is always concentrated on some point. And basically, if I don't exhaust whole graph, I just see a path of length to r. Or in terms of vertices, this will be path with 2r plus 1 vertices, because I just use index for the number of vertices. So this happens if I don't exhaust n. If 2r plus 1 is smaller, okay, I have to also not, should be smaller than n, yeah. If at least one vertex is not reached, and otherwise I see the whole cycle. This is Cn otherwise. So in this case, it happens that my measure is just concentrated on single graph. It's either a path or a cycle. Yeah, and so we'll see more example soon. And then there's observation, maybe I'll call it a lemma. So a sequence Gn is locally convergent in the way I defined before. If and only if for every radius r, if I look at sequence of measures, then this converges. And in this case, I call the limit rho of r. In generally, when you talk about convergence of measures, you have to be careful what exactly you mean. There are different notions. But here, like if you give me a radius r, there are only finitely many different graphs you can see at distance r, because maximum degree is at most d. So support of this measure is at most, say, roughly d plus 1 to r. So it's a measure on a finite set. And then like all notions of convergence, they're equivalent. It doesn't matter which one you use. You can say probability to see any particular graph is the same. It converges to some number. Yeah, and one implication is it's easy, because in some sense, suppose I choose R such that I can fit my copy of F inside ball of radius R, or more precisely inside F, if I can find a vertex X such that every other vertex is distance at most R, then basically whenever I pick R, so each copy of F would be lying in some R ball. And if I know statistic of R balls, I can kind of see how many copies of F I have. It requires a bit of counting, but this direction is easy, and conversely is also true. Like inside bounded degree graphs, if you know this T star densities, then also you can recover like distributions on balls, again by some kind of inclusion exclusion, if you do it carefully. So, there are like two equivalent ways to define this convergence. So now I would like to give some examples. So let's draw a table. So first I have some sequence Gn. Then I have this sigma r. And why it's kind of this rho r? Why these both statistics are more convenient? In some sense, each one contains more information. So if I know what I see, if I look distance r plus 1, then I can just sample ball of radius r plus 1, and I can remove all vertices at distance more than r. So I know what is distribution on r balls. So somehow, okay, so sigma r plus 1, or rho r plus 1 determines rho r. So there is some kind of consistency condition, and you can write it easily. And then it's known if I have like sequence of measures like this, which are consistent, then also I can define a measure which I'll call rho infinity, which would be a measure on infinite graphs up to isomorphism. So somehow then if I have a convergence, I can define rho infinity, which will be a probability measure countable, connected, possibly infinite graphs. Connected, possibly infinite G. Again, maximum degree is at most D everywhere. Here you have to be a bit careful. Okay, if the set is countable, if your support is countable, it's fine. But this set in general is uncountable. You might have like continue many non-isomorphic graphs G. Then you have to be a bit more careful what are measurable events, but yeah, I'll just ignore these issues. Yeah, so there's like well-defined way how to define this rho infinity. And so, for example, here, like, let's look at some examples. I'll need two more lines. One would be rho, and then this will be graphing. So that will be another way how to represent this limit. Okay, so suppose I look at this example Cn. Then we argued as before. So if I take a radius r and then n goes to infinity, I just see only paths when I travel r in each direction. So each rho r would be supported on this path, whose number of edges is to r, pass on to r plus 1 vertices. And what will be your infinite graph? Well, it will also be a Dirac measure. It will be supported on just infinite paths. But if you remember, each of these graphs is a root, has a root. Similar, if you look like limit of paths, Pn, it will be the same. Maybe let's look one when it's a bit more complicated. So suppose my graph of length n is as follows. I take path of length n, and to each vertex I attach a leaf, a pendant edge. So for n, I take n like com. Then what happens in the limit if I pick any r? So if r happens to be on the top, then basically I can go in direction r in each direction. And then at some point before the end, I could go down. So that's what I see. And I see this is probability 1/2. So now it's not a Dirac measure, it's supported on two types. Also with probability 1/2, maybe if I pick random vertex, I end in the bottom. Then my graph would look like this. Well, I can, from the bottom, I can only make step up. And then I have r minus 1 steps to do. So here I go distance r minus 1 either way. And sometime, anytime early, I can just go down. And this also has probability 1/2. So what would be like distribution on countable graphs? Well, it will also be supported on two elements only. So one will be infinite com, where my root is at the top, so it continues to infinity. And the other one will be infinite com, but my root is at the bottom. So both of these sequence converge, and in this second row of this table, this kind of countable limit as a countable distribution countable graphs, it's supported on two elements. So let's look at another example. Suppose my graph Gn is d-regular, which means every vertex has degree d, and but now it has no short cycles. So it means girth goes to infinity. So the length of shortest cycle goes to infinity. So for example, you can find graphs which are irregular of order n, where the shortest cycle has length only log n. It has no short cycles. Yeah, it takes some time, like random irregular graphs will do. So in this case, what is, if you pick a random point and you go distance r, you don't see any cycle, and graph is regular, so what you are going to see would be tree of depth r, which is d regular. I just draw case d equal 3. So you continue, you go with until depth exactly r. So here r is equal to. And yeah, as a limit on countable graphs distribution, you will just get again a Dirac function, which is always equal rooted irregular tree. It's a bit different from binary tree because in binary tree, root had a different degree, but now root has the same degree as everybody else in this example. So here d equals 3 for illustration, and r equal 2. Yeah. Any questions? Maybe let me pause. And you can easily get more complicated distributions. For example, this row infinity could have a support of size continuum quite easily. Because the graphs which I considered here, like in some sense, are very homogeneous. And so the question is, yeah, what will be like limit object here? Okay, of course, I can work with this row infinity, and in many cases, yeah, it's very useful. But then another, maybe, is there some other representation? And indeed, there is. It's called a graphing. So it will be a quadruple. So I'll just write first all terms and then try to explain each one by one. So first, yeah, we have V as a set of vertices. And it would be usually typically continuum, and you can assume it's a 0, 1 interval. Actually, in every case, by some isomorphism, we can assume, as far as local convergence is concerned, that it's a 0 unit interval 0, 1. Then if I looked at V beta mu, so this would be standard probability space. And again, you can assume that this is just unit interval. This beta set of measurable sets. These are just Borel sets. And then mu is Lebesgue measure, or uniform measure on the interval. So somehow, when you construct limit objects, like if you can always assume that. And then, so what we have finally, VE is a graph, but not just any graph. So it's so-called measure preserving graph. And maybe I don't have time to give definitions, but if I have time, I come later. Let me try to give you some examples in the right corner. So I have basically probability space, unit interval with Lebesgue measure. So I have some graph which will be bounded with maximum degree is at most d. And it's not just any graph. In some sense, it has to be well defined. And also, it has to be measure preserving. So if I have a chance, I'll say a few words. Maybe before I move to this property, let me try to give some possible examples of limits. And so what it means, so Gn locally converges to this. Well, I can define this Arbol statistics. Maybe call this H. So what will be my Arbol sampling? Well, I have probability space, so I can just sample point X in V, distributed accordingly to measure mu. Then I forget about measure. I just look at the graph and I see what is distance r from me in the graph, and that's my output. So what I do, I take ball, I look at my graph, which is VE, root is X, and I just go distance r. And for example, if you have finite graph, you can take uniform measure on its vertex set, you get the same definition. If you want to have a vertex set to be equal 0, 1, you can just take many copies of your graph. So it includes finite graphs. Okay, maybe let me just tell it here. So finite G. Maybe just suppose it's just you pass. How can I make a graphing? Well, I can partition my interval into 3 parts. So this is my unit interval 0, 1. And then I can, so these points would be 1/3 and 2/3. And what would be my edges if I have X in the first or second part? I connect it by edge to X plus 1/3. And so on. So I would have like between every 2 parts, I would have a matching. And then, so it's again connected. This third point is x plus 2/3. And for example, if I pick a random point here, well, it's equally likely to be of any of these three parts. And similar, and what I see is just this path of length 2, which is exactly what I would see in the finite graph. Yes, so if I would like finite graph G, I can represent it as a graphing. But there are many more than just finite graphs. So for example, how I would like maybe just to take a few more minutes just to fill this table. So what can I take? I want to have some probability space in some graph such that if I pick random point, I see infinite double ray. And one way is the following. I can take unit cycle. So my vertex set is unit cycle. I call it S1. And what are my edges? Well, total lengths, let be, or maybe even, let's just work with interval 0, 1. So I work like modulo 1. So I can see the unit interval modulo 1. And then what are my edges? I fix some irrational alpha, maybe say square root 2, doesn't matter. And then I connect x to x plus this alpha modulo 1. I'm not sure if it's visible. So I fix some irrational angle modulo 2 pi in this geometric picture. And every one I connect distance alpha. So if I go along this, I never come to the same point. Or similarly here, if I look at this mod 1 representation, when I start with x, if I go backward or forward, I never come back to the same place. Except I just go backward and forward. Yeah, and here it preserves the measure because in this notation of a circle, I just rotate it. It's clearly a measure preserving map. But there are many others. So for example, another way you can take any other transformation which doesn't have finite orbits, which is measure preserving. For example, a shift on 0, 1 sequences to be a different representation. So what would be an example of graphing for the second line? So we have two vertices of two special kinds. So one option would be you take two circles. On the first one, you take the same irrational rotation graph. So that's like top line. It's each has measure 1/2. And on the second, and additionally, you want to have like the pendant edges. So you just map x here to correspond. You just put a matching. Just move it. So if it's, so you just put a perfect matching, and that's an example of a graphing, which is the limit of this sequence. Because if you pick a point, it's in one of the circles, and then, like I say, on the left, and what you see on the left, you see infinite paths, and on each point you can move across, but then you stop. So this is exactly the picture which we saw here. And last example, okay, d equals 3. How can we make the space? Well, here would be convenient to do some geometry. What you can imagine that your vertex set is S2 with usual surface measure. So all rotations, reflections preserve the measure. And and then what we do, we take some random rotation or generic rotation. Which plus we take we want it to be, so we connect x to images by this rotation, so it's to regular graph, and this will be another example for line 1 if you like. So occasionally you would see like measure 0 of points where your rotation fixes your point or something like this, but this would have measure 0. But then we wanted to add make it 3 regular and look almost everywhere as 3 regular tree. So what you can do, you can add, maybe call it gamma 1, this rotation, and then you can take a reflection among, say, z-axis. Reflection gamma 2, maybe it just maps set coordinates to, so which maps, say, x, y, z. Say it keeps x, y, and but reflects z. And then what are your edges? You can see the pairs x when you apply one of these gamma i's to x. And then if you see this graph will be 3 regular, you can apply gamma 1 inverse, gamma 1, and gamma 2 is involution. So gamma 2 inverse is the same as gamma 2. So this graph is 3 regular. And apart some countably many exceptions, if you pick a random point and follow these gammas, you never come back. So what you see would be 3 regular tree. Yeah, and then just maybe to finish for today, yeah. And then one result is basically that for every locally convergent sequence of bounded degree graph, there exists a graphing which is its limit. So this was proved by Aldous and Lyons and independently by Oleg. In 2007, I believe, both papers appeared. Yeah, and for example, Badendra, so maybe just to say a few words. So here it was an open question where every graphing can appear as a limit of finite graphs. And this was recently disproved, but proof is very complicated. So somehow we still don't understand which graphings are possible limits. And maybe just instead of given definition, well, I said we require this property of being measure preserving. And where it comes from, well, one definition would be if you take any matching in your graph, then it should preserve the measure. And in finite world, it corresponds to the fact that if you have any bijection, then it preserves sizes. And so in the limit, this property has to carry over. And yes, and so we know each sequence has a graphing, but it's still like widely open which graphings come from finite sequences. And also there are like usually many choices. Like for example, in this line 1, yeah, we could take this solution, but only use gamma 1, not gamma 2. That would be another like limit graphing. And so like quite interesting question is, yeah, can you encode more information about graphs? Yeah, and there are like some partial results. You can also include some global structure. So it's called global local convergence. Yeah, and these objects also appear in ergodic theory and like measurable group theory. because basically equivalent definition of a graphing, which would be exactly what we're doing in this table. You just take some measure space, standard probability space, and you take some number of measure preserving maps, and you take, I put an edge between if my x and y are connected by one of these maps. And this is exactly what generates set of graphings. So so we know, yeah, there are different ways to generate graphings, but big question would be, yeah, which one comes as limit of finite graphs? Yeah, I think so. I'm a bit over time, so I'll stop here. So yeah, thank you for taking this course. I hope it was useful.